Before I get into this, I do want to warn that everything I'm going to describe is perhaps what we would call, like, is typical. But like I've been emphasizing, do whatever you want, okay? I will say, like, well, in this scenario, these are the things you might want to use. That doesn't mean, oh, those are the things I got to use. No, no, no. Just, I'm showing you what might be typical as a good starting point if you're kind of lost. So, we're going to talk about different, common different representations, especially in the context of a genetic algorithm, and maybe what might be appropriate genetic operators for those representations. So, the different representations, defining the representation is like one of the first steps you're going to do. How do I want to encode my problem? Depending on your problem, you might have many obvious choices, or you might have one obvious choice, or anywhere in between. So it's not a trivial thing, but for example, with TSP, it makes sense to perhaps have that permutation, that string of cities, right? The ordering that you visit them. Makes perfect sense. There's nothing stopping you from having a different encoding. It's just, if you have the permutation of cities, you think of like what the genetic operators are doing to your candidate solutions. If you come up with a different encoding, maybe the encoding is, no, we'll have like one default order, which is like 0, 1, 2, 3, 4, all the way to the end. And then your chromosomes are like how to maybe shuffle that default one. The genetic operators can have like a wildly different impact on how the evolution will perform. So there's a lot of choices you've got. So there's a bunch of types of different representation, and the common basic ones are binary, which I believe was the first one anyone ever used for a genetic algorithm. Integer, real value, floating point values, permutations, a tree representation, that's your standard genetic GP, genetic programming. And the list goes on, you can do whatever the heck you want. There's evolutionary strategies, which I'm pretty sure uses finite state machines, very simple form of model of a computer, and then you modify those, but you could do whatever. The binary encoding, actually, it's an interesting history. Genetic algorithms, or the idea of evolutionary computation, is really old. Alan Turing basically like proposed it. He called it like evolving, I can't remember what he called it, but he like proposed it. And then concurrently, multiple researchers kind of invented their own variation of that. Like there were genetic algorithm, evolutionary strategies, and then another one, I can't quite remember what it is, but they all kind of like evolved separately, but in the end, you know, they all published their work and they're all like, hey, it's like the same thing, isn't that neat? It was interesting, actually, back when I was at so GAs, which are by far the most popular, they were invented by, I can't remember their name, Goldsmith, I want to say, but I don't think that's right. They were at University of Michigan when they were, like that's where they came from, was University of Michigan. So I did my PhD at Western, which is, you know, down a long road to Detroit, and like the 401. So, it's the 401, right? Southern Ontario people, I'm right? Yeah, all right. So, it was a committee member, not my supervisor, but one of my committee members, what's his name? Oh, it's bad that I can't remember his name right now. But when he was a graduate student, was also inventing his version of an evolutionary computation algorithm. It's just that he was just a little bit behind the other guys, that his kind of got lost in the noise, and he's not considered one of like the founding members of evolutionary computation because he was so close. Which, that's got to be a real piss off, right? Imagine being that close to being like whoa, that guy, right? Anyways, fun little anecdote. So if you go back in time, binary representation is like the first one. So here, binary representation, we've got some encoding for a problem, a bunch of zeros and ones. What those zeros and ones mean, well, that depends on your decoding and what the heck that that means. Does it mean like integers? Does it mean characters? Does it mean whatever? It's just some encoding that has some decoding. So string of zeros and ones, it's the earliest representation. It's great if you maybe have like a series of Boolean decisions to make, but you could do anything. You could take a binary string that gets decoded to a city permutation. You could totally do that. There's nothing wrong with that. It would probably suck, but you could do it. And yeah, you can encode whatever you want with it. See, look at that perfect encoding for a problem I have in mind, right? You don't know what it is, neither do I, but it can encode whatever. And there's actually some interesting, they call it like schema theory. There's some interesting proofs about convergence, I believe, when you use a binary representation that you can't, or they haven't proven about a more general representation. There's some neat, cool things you get with a binary representation, but a binary representation is very limited. Because what do you think is going to be easier? Using that to mean a series of cities, or maybe just, an ordered string of cities? Probably the latter, right? So, could be a problem because of the difference between, like, what the distance, like that example of optimizing the number of ones. A little change in the genotype space, flipping one bit, what does that mean in the phenotype space? Does a little change mean drastic changes over there? Or does it mean little changes over there? Or could it mean a drastic change over there or a little change over there? With the string of zeros and ones, it kind of had both, right? A little change might make the number go from 0 to 16 right off the bat. Or it might go from 16 to 17. So like it's a fairly chunky translation of like what the distance in this space versus the distance in that space means. So yeah, Hamming distance, that's what we were talking about. Raise your hand if you've heard Hamming distance before. Couple people, you know what it is, we talked about it before. I would say the distance between these two values is 2. Because how many changes do I have to make it match? There are other things too, like Levenshtein distances, which allow like rotations and flips and whatnot. Be careful on how you define that. But anyways, Hamming distance, it's simple. If it has a distance of 1, that's a small distance. If I had a series of 1s and a series of 0s, that'd be a very big distance. So, the mutation, a good mutation when you have a binary string, bit flip. It's easy. It's a pretty standard. Just if it's a 0, make it a 1. If it's a 1, make it a 0. You could have a probability to perform mutation like we did, like a 10% chance, whatever. Perhaps randomly select how many bits to flip to. Maybe instead of just 1 bit, we'll say like flip somewhere between 0 and 5 bits. We could do that. There's nothing stopping us. Sky's the limit, right? Remember, all of this is just the high-level framework. How you implement it, whatever the hell you want. Get creative. So yeah, here's an example. Look, it looks like I flipped 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. Cool. Is that a good thing? Well, it depends on the problem. Crossover, 1-point crossover is great, which is that. Find a point, flip them, great. Do endpoint crossover. You pick an arbitrary number of points and then flip between like every other like post. See? It's best described as that picture, I think, right? Yeah, yeah. Uniform crossover. Here's another one. So 1-point crossover and like 2-point crossover are common-ish, I guess. Endpoint in general is as well, but if you increase n, well, okay, uniform crossover is you basically flip a coin, like you have a 50-50 chance every time, or maybe you don't want it to be 50-50 chance. Maybe it's some probabilistic chance to flip each one. Just basically like a giant number of mutations potentially. That's uniform crossover. So your 1 point, your n-type, your uniform, these are common crossovers. Which genetic operators are best? There's no answer to that question. It depends on your problem, depends on what works for your problem, and a lot of times, you might have some intuition on what would be good and what would be bad, but sometimes you don't. Sometimes it's, I don't know, let's just try this. Is it working? All right, cool, good enough. It depends. Is mutation better than crossover? It depends. It also depends on the time of evolution, right? Remember when we saw yesterday, where crossover, once you have no diversity, that 1 point crossover is actually kind of terrible. So mutation becomes more important later in evolution in that particular scenario, but not all scenarios.
What's genetic operator again?
Mutation, that's the one where the modification is to a single chromosome, where crossover, that involves 2. That's like the 1 point.
Different kinds of crossover or otherwise?
No, mutation's not another type of crossover. Mutation is just... Mutation is just you make a modification to a single one. Crossover involves transferring information between 2.
So by genetic operator you mean mutation?
No, genetic operator means both crossover mutation.
Okay.
Yeah. Okay, exploration. Find new areas of the search space exploitation. Use what we already know is good and look around there. These are 2 common terms that aren't that's what they mean, but you can easily make an argument that exploration means mutation, right? If your mutation makes a change, you might make a big jump to another part of the space, you're exploring. But you could also make the same argument that your mutation could be very exploitive. Well, I've got 1 chromosome that's reasonably good, so why don't I just make small changes to it so it exploits what's already good? But maybe we could call crossover very exploitive because while crossover I've got 2 that are good, well maybe, or maybe it's exploring because depending on how destructive our crossover is, it might make big jumps in the search space. I'll talk about destruction when we talk about the permutation ones. It's good there. So sometimes you'll hear evolutionary computation researchers argue over no, that means mutation. No, it doesn't. It depends on what it means in the problem that you're dealing with. They are wrong, don't listen to them. Listen to me. Yeah. This is me basically saying, whatever, it depends. All right, integer representation, okay. Maybe only from a predefined set, like allowable genes are integers between 0 and 100. Maybe 0 to 3, okay. Let's say, do I have a picture of that? No, I do not, sadly. So maybe what I want to do is create an encoding for a little robot to go through a maze, and I want to evolve the path for the robot through that maze. So maybe my representation is 0 through 3, that gets decoded as northeast, southwest. Could be another decode, whatever, it doesn't matter. But we can have an integer encoding that means whatever we want. So far in the examples, we've seen the Boolean, or the binary, and the permutation one because TSP and N queens, but also think of the matrix representation of N queens, right? It's not really, I guess we could argue it could be a binary representation because it's 0s and 1s, but we just stack them. Maybe we could argue it's a whole different type of representation because it's not really a string, it's a matrix. What I mean here is, if you come up with a representation it doesn't need to fit in one of these categories. It doesn't need to be binary. It doesn't need to be integer. It doesn't need to be permutation. Just use whatever works. Yeah. Creep mutation. So you could do a bit flip, of course, here. There's nothing stopping you. But creep mutation. Change a bit flip. That would be single point mutation. Single point mutation is the generalization of a bit flip. Single point mutation is find a single spot and make a change to it. If it's binary, well, it's a bit flip because it's just, if it's a 0, make it a 1. But if it's 0 through 3, well, you pick a spot and then, I don't know, maybe randomly pick, maybe you add 1 to it, I don't know. Okay, so creep mutation, change value to 1 close to the current value. So this would be an example of, I've got some encoding and I pick an index that I want to change and its value is 7. Maybe I make it 8. I could make it like 70, but that's a kind of a big jump. So maybe depending on what the values mean, what they decode to, we want like, well, we don't want it to make big jumps. We want the jumps to be small. And yeah, I'm trying to think of a good example, but I don't really see a lot of integer representations. So it's hard to come up with a good example. Whatever. I'm sure there's a billion, I just can't think of any on the spot. Use same mutation and crossovers binary representation. Oh yeah, that's what we just said. But again, come up with whatever you want. And this isn't hard, right? Like, how do I want to modify this? I don't know, just shuffle it, maybe? Maybe your mutation is do a quick little shuffle. It's probably very destructive, because if order matters and you do a shuffle, that could really obliterate any good value, but you could do it. Yeah. Oh, and yeah, there are people that like can get a PhD and like, I came up with a new crossover for this very specific problem in this very specific case. Like, that's legit. Like, it's a huge area of research. People do that stuff. Real values, maybe we want to encode real continuous values. Typically, genetic algorithms aren't particularly good with real values. They're fine, but there are other forms of evolutionary computation that are more designed for real values, like differential evolution. Sky's the limit. But GAs, they're not designed for real values like other forms, but we could totally use it. I can use a GA to maybe encode weights for a neural network. Evolutionary neural networks, great. I evolve the weights with real values here. Maybe I'm encoding the size of a satellite dish, like people have done at NASA. Some forms of EC are better here than others. GA, yeah, there we go. They're not great for it. Ackley's function. So this is a classic toy problem people will use. I've never actually used it, but it's a classic toy problem. If I'm trying to minimize this, so this is the function, you know, in this space. And I'm going to guess the z-axis here is the fitness value. And let's say I'm trying to minimize. That search space is the 2 dimensions, and then up and down is like fitness. Clearly the best point in here would be wherever that is. But you can see that there are a lot of local minima. Assuming we're minimizing this problem. We're looking for the smallest, smaller fitness is better in this scenario. That is a terrible space. It's like designed, it's used because it is deliberately, it's so easy to get your algorithm stuck in a local minimum maximum that it's trouble. So if your algorithm can always find the maximum, or minimum, that's wonderful. But here, this would be dealing with real values. So uniform mutation, it's kind of like bitflip. Take a value from a uniform distribution within some defined range. I have some uniform distribution. Here, raise your hand if you remember what that means. Okay, it's just like it's like rolling a die, right? Oh, it's a 1. Oh, it's a 6. You have equal chance for all of them. Just randomly pick a new value with equal chance. Then you can have non-uniform distributions, but instead of a uniform distribution, maybe you have a Gaussian distribution, right? Your bell curve, that normal distribution, right? Where instead of having your distribution be okay, if I pick an index and I want to make a change, instead of just having the likelihood of changing it to a 1 is this, the likelihood of changing it to a 2 is this, the 3 is this, assume they're all the same height, and so on, where maybe instead I've got a distribution like this, where I don't know, maybe this is like 10. So you're very likely, if I make a change, I'll pick a new number from that distribution with probability of that. So here, yeah, I'm very likely to maybe change it to a 10, or numbers near 10, but I become less likely to change numbers the further we get away from 10, which might be a good thing. And like maybe we really need something to be like a -4 in a given index. But maybe that's very rare, so we want it to be rare. One, there is no test, but two, like this, if there was a test in this class, memorizing, oh, this function, like, no, that doesn't matter. Just, I'm telling you these different ideas to give you a sense of like, oh, okay, those are the ideas people use, where can I go with this? And of course, stop me at any given point in time. Is this boring to a lot of people? It's kind of boring to me. No, you like it? All right. Yeah. Replace the gene with a new value. Self-adapted mutation. Here's another one. What should the values be for creating a Gaussian distribution? Okay, no, you know what? No. Skip this one. This one's insane. This one's basically like, wow, what if our mutation defines a way to change what the distribution should look like at different points in the... Yeah, you can do that, but I wouldn't. It's just kind of hard. Uncorrelated mutation with 1 step size. I don't even remember what these are. Uncorrelated mutation with n step size. Correlated mutation. I don't know what those are, but they exist, and they're different strategies. I can tell you right now, they're not very popular. I don't think I've never used them, and I don't think I've read a paper where anyone ever used them, but they exist. I'm sure they're really good at solving problem X, Y, Z. Real value crossover. Yeah?
So if you were to have an encoding, say like a vector of integers, would that fall under integer representation or real value representation?
If you want it to be a vector of only integers and you only ever want integers in there, I'd call it like integer representation. Yeah. Yeah. Shoot, I just had a thought. What was it? Those ones. Hold on. I had a good thought based on what you just said, and it immediately left my mind. Okay, no, I remember what it is. And depending on timing today, I might cover it. Remember graph coloring, okay? Just remind me that later, and I'll try to describe that problem and maybe a good encoding for GA. All right, crossover. Real value representation crossover. So discrete. Offspring have values from one parent. They're easy. We've seen them before. 1-point crossover, right? If they're real values, pick the point, do 1-point crossover, n-point crossover, uniform crossover. They're all fair game. But that might not make sense. That might not make sense in the context of your problem, where you might have values like between. Remember, these are real values. So maybe, you know, like that precision, the decimal, maybe they really matter in your case. And maybe it's not about making these jumps, it's about making these like kind of continuous movements through the space instead of like jumps. Because when you think of TSP, if you think of that search space, every step you take in like fitness is going to be like a discrete step away, where in continuous spaces where you have real values, could be very different. So, single arithmetic recombination. Pick a gene and average the values between them. There. I picked this one, I guess, and I guess the value between them is 0.5. There. Cool. There is an example of a real value crossover. The point isn't for you to go, oh, I better remember this. The point is for you to go, oh, interesting. I guess that is a funny way to do crossover, where before 1-point crossover, perhaps very intuitive. This might be less intuitive, but as soon as you kind of see it, you go like, oh yeah, I guess that would make sense. Why couldn't you do that? Yeah, do whatever. Simple arithmetic recombination, pick an index, average values after that index. That's like the same thing, except instead of like a single point flip, it's kind of like 1-point crossover, except with the averaging strategy. Whole arithmetic, do the whole thing, great. Cool. Now for permutation. These ones pop up a lot where order matters. we've already seen a couple examples like TSP and queens. They've got great permutation representations. This is where the order can also really, really, really matter, right? Think of TSP. It's not where a given city lies in that string. It's where that city lies relative to the other cities. That's what matters here. The consequence of going from city 7 to city 77 versus 7 to city 52 could be wildly different. It's that adjacency between the two. That's what's important here, and that often comes up a lot of times in permutation combinations. Maybe I shouldn't say often, but it frequently does. Like, it can come up. TSP, classic example of that. It's not where it is in the string, it's where it is relative to the other values. And this note on the lack of independence between the strings, like they depend on each other in terms of the fitness, this is where it becomes a little easier to talk about the idea of destruction. If I have, so you remember that example crossover I showed you, that partially mapped crossover about how you deal with situations when you need your chromosomes to only have unique integers in it, right? Like TSP. Because with TSP, if I have the string of cities that's like 7, 4, 3, 8, 6, right? And I did crossover with 8, 4, 3, 6, 7. Like if I did crossover here, this 7 goes up here, that 6 goes down there, the 8, the 3s, whatever. But the problem is I now have 2 8s, and this one has 2 8s and no 7. This one has 2 7s and no 8s. Like that's bad. So we had that partially mapped crossover, which is a way to kind of deal with that scenario, where you go, okay, do the crossover, but if it already exists there, you like skip it and you keep going and you loop back around. We will cover that again very shortly. But have that in mind and think, and while also, like when we see that, what I want you to consider is, remember, it's like the relative positioning of the cities that matter. Okay. So TSP, it's easy to represent these problems as permutations. For some of these problems, it's not order as much as it is the adjacency. All right, well, that's what I just ranted about. Pay special attention to how some of the genetic operators impact the adjacency. Yes. TSP. I don't know, what is that? The Netherlands? Yeah? All right, cool. So there's a bunch of cities in the Netherlands. What's the fastest way to hit them all, right? Assuming you can fly. Like, we don't need to deal with stuff. You know, right? You don't need to like, whatever, I can just fly over that water. Yeah, thank you. That's the words I meant. I mean, we could change it to actually be road distances, but whatever. So, a lot of the previous examples are problematic because it might cause issues with the uniqueness of the values in our permutation. So we need a permutation of unique cities. So if we do single point crossover, we could be in big trouble like I just showed you. And if we change a gene, we will get a repeat city, right? So that's why we talked about before, we did like a pick 2 and then swap mutation, not pick a single city and change its value. Because if you do that, you're already screwed. You're now, if you ensure that the value that you're changing it, like if it's city 7, you got to pick a new city, but it's not allowed to be 7, well then you're guaranteed to get a duplicate value somewhere. Whatever city you pick to put in that index, that city will exist in your string, in your permutation. That makes sense, correct? Good. So we need to have better ideas here. Better is perhaps not a good word. We need to have different ideas here. So swap mutation is great. Pick 2, swap them. No risk of destroying the permutation property. If I've got a string of unique numbers, if I pick this one, swap them, there's no way to add a new number in there that just screws anything up. We're fine. So yeah, swap mutation. Insert. Pick 2 genes and add one after the other. Again, no risk. Perfect, I picked this one, all right, put the 5 after it. It's a slight variation, yeah.
Maybe I just didn't see the diagram for swap, but I don't see how swap doesn't destroy it. Because if you're swapping them, right? Oh, you mean swap? Okay.
Yeah, there you go. See, these are a lot easier to describe with pictures. Do that.
I was already thinking of insert.
Do this. Great. Scramble. Pick a subset. Scramble them. Cool. This is just a bigger version of like swap, really. It's just do it in more spots. Inversion. Pick a subset and reverse it. That's an interesting one. In fact, we'll come back to this one. So pick 2 points. Okay. What's cool about this one is it preserves a lot of the adjacency, where it'll break the adjacency at the 2 points I pick. So inversion is I got a string, pick this point, and then flip it. Okay? The adjacency of all those values, if that was a good permutation, if that was a good ordering, maybe this chunk here that I'm about to flip, that adjacency was really important. That was a really good path to hit cities, whatever these were, in a minimal way. So if I flip it, I cause a drastic change over here and over here, but everything here is kind of left as is, and it preserves that orderness. And that is an example of a not particularly destructive mutation. We're not just obliterating the adjacency. Where if we did something like scramble, where you just pick a chunk and then just change them all, that's fairly destructive in the context of TSP, because any adjacency that was there, which is kind of what we're evolving, right? We're evolving good adjacencies of those cities. So if that chunk there is presumably a reasonably good order, and we just scramble it, but maybe we'll get lucky, because maybe, if we think back here, realistically, if we have a contiguous chunk that's a really good ordering, it's probably going to correspond to like chunks that are close, right? Like it's going to want to go to close cities. So maybe it's like this set right here. Where maybe if I take that group and I shuffle the ordering, maybe it actually doesn't matter so much because they're all still close to each other. All of these terms are very hard to use in absolutes when working in this space, in this realm. Of like, oh, it's very destructive. Is it though? Like, does that matter here? It seems like it should matter, but then again, when you think of it that way, maybe it doesn't matter so much. This is why be very wary of any computer or evolutionary computation person that just starts making assertions about anything. Because we can't. Because we can't like prove anything about this stuff. We hit run, we cross our fingers and hope for the best. It works. I can't prove it. I can prove it empirically. I can be like, see, it's good. Yeah.
Do you still want to talk about graph color?
I do, but what time is it?
2. Oh, around 58.
Permutation. Let's see how close I am to the end here. Ooh. Wait, I went too far. Ordered crossover, mutation, okay, inversion, and now we're here.
Creates graph about half percentage of slides skipped.
32, okay. Let's see if I can. I'm going to try to explain the graph coloring thing. Has anyone heard of the graph coloring problem? A couple people. Basically, the idea is, if I have, how well can the people, can you see? Like, Matt, if I draw here, could you see, or is it going to be giant glare?
No, I can't see. Maybe you could choose like a darker color, like red, maybe?
The red, maybe, yeah.
Maybe the red.
Oh yeah.
Yeah.
Yeah, all right, cool. Ignore the actual color that I'm using. The idea is if I have a graph, some arbitrary graph, what I want to do is find the minimal coloring, where the goal is you pick, I'm going to start with node, I'm going to color it with an X because I don't have colors. So now I'm going to go to another node. I need to pick another color that isn't one that is adjacent to the same color. I'm tired. I'm not making much sense. I could word that better. If this is an X, this can't be an X. This could be an X. This can't because it's touching this. So this needs to be a happy face. And now this, it can't be a happy face or an X, right? So this needs to be a sad face. The sad face color. Now here we can go with a happy face because I want to pick the minimal number of colors I need to color this graph. This is a very challenging problem. You could use a GA for this, but how would you encode that? I mean, that's more rhetorical. I can do an X here. I can do a sad face here. Here I can do a happy face. Uh-oh. I can't do a happy face. I'm touching a happy face there. Shoot. Looks like I need a fourth color, right? Shoot. What should the fourth color be? Come on, let's have
Straight face. I know.
a straight face. Indifferent. And then this can be an X, I guess. So the way I did the coloring is, well, I could do it with 4. I might, maybe you could color this with 3, you know? I don't know. One, two, three, 4. It looks like it might be connected to the degree where you need at least, but then again, maybe not, because whatever. In fact, let's go here. If I could change this happy face.
Well, can you flip the X and the sad face at the top?
Those two?
Or, no, because never mind. Or change the...
No,
the
yes,
X.
I can. I can do this.
Yeah, we'll change that one to a happy face, maybe.
There, if I do this a happy face, we're still good.
Yeah.
Turn this to an X, we're still good. Now I can do this as a sad face.
And then X.
Now it's 3 colors. I didn't need the straight face. Ooh, it's better. Of course, as you can imagine, as this problem gets, as the graph gets bigger and bigger and bigger, it becomes a little difficult to manage. But how could I encode a GA to do this coloring? I don't know. Don't answer it. If you have, did anyone look, okay, for those that, raise your hand if you've read assignment 1. Okay. Did anyone, so raise your hand if you think yeah, I've got a reasonably good idea about the TSP problem. I understand it. No? Okay. Not understand how to find a good solution or anything, but understand what it means. I've just got a list of cities. Yeah, okay. Did anyone read an example of the, what was it called? Delivery problem? Vehicle routing, thank you. Did anyone read into that?
The first thing that popped up on Google.
Yeah. So coming up with encoding for that is really tricky. I remember when I was in grad school, I took an evolutionary computation course. No. Something about evolutionary computation. But it was a fairly advanced version. And we were studying that problem. And I came up with a really good encoding, and I was so proud of myself. The prof was like, wow, this is so good. I was so proud of myself. It's tricky, though. But I would encourage you to try it. Even if you try and you don't succeed, it'd be really good experience to get you thinking about how encodings matter and how there are some problems where there's no obvious encoding off the bat. Yeah. Cool. And the cool thing about vehicle routing is it's what we call a multi-objective problem, which is that example of teddy bear factories and worker deaths, right? Sometimes things you want to optimize might be at odds. Sometimes they might be kind of there's a synergy between them where you want to maximize teddy bear output and teddy bear fluff input. I don't know. As you increase one, you'll increase the other. I don't know why you would want to do that, but but sometimes they can be antagonistic. Anyways, whatever. Go home if you can. See you later. Relax this weekend.